You ever think about what a molecule's true identity is? I mean, we see a chemical formula, something like H2O, and we think, yep, water, got it. But what if I told you that simple formula is just, well, it's just the beginning of the story? That the real identity is actually hidden in plain sight? So that's the big question we're tackling today, because it turns out, in the world of chemistry, a molecule's identity, we're talking its name, its behavior, everything about it, is tied not just to what it's made of, but to its unique shape and structure. Okay, so how in the world do chemists keep all of these identities straight? Well, they've got a system for that. It's like a kind of chemical passport control called nomenclature. And we're going to dive into a really fascinating part of it, how to name these ring-like or cyclic compounds. So the very first thing you have to figure out is kind of a power struggle. When you've got a ring with a chain of carbons hanging off of it, which one gets to be the parent? You know, the one that gives the molecule its last name? It all just comes down to a simple count. This slide lays it out perfectly. So look on the left. The ring has 3 carbons, and so does the chain. It's a tie. And in a tie, the ring always wins. It gets to be the parent. So the name is propylcyclopropane. But now look at the right. The chain has 4 carbons, which is more than the ring's 3. So the chain takes over as the parent, and the ring just becomes an attachment. And the name totally flips to 1-cyclopropylbutane. See how that works? And, to make that identity even more precise, certain groups of atoms, what we call functional groups, they act like VIPs. Think of something like the OH group in an alcohol. That little group gives the molecule its whole personality. So it gets priority seating, it gets the lowest possible number in the naming sequence, and all these rules make sure every single molecule has one, and only one, unique, unambiguous name. Okay, so just when we think we've got this whole identity thing figured out with all these precise rules, chemistry throws us a curveball. We're talking a real mystery of molecular doppelganger. So we just established this, right? This is the key point. One structure, one name. That's the foundation of chemical identity. Seems pretty straightforward?
But then, you see this, a single molecular formula, 4 carbons, 10 hydrogens, C4H10. Now, based on what we just said, this should describe exactly one molecule, right? One identity. But does it?
And here is that puzzle in action. C4H10 can be N-butane, just a straight, simple chain of 4 carbons, or it can be isobutane, a shorter 3-carbon chain with a branch. They have the exact same list of ingredients, but they're built in completely different ways. They are 2 totally distinct molecules that share one single formula. Now, this whole phenomenon has a name. It's called isomerism. And here is the part of the definition that people so often forget. It's not just about having a different drawing on a piece of paper. It's about having genuinely different properties out in the real world. And that right there is the absolute heart of it. N-butane and isobutane, they have different boiling points, different densities. And why? Well, because N-butane has this straight shape, the molecules can pack together really neatly, kind of like logs, and that creates stronger attractions between them. But isobutane with its branched shape is bulkier. It can't pack as tightly. That real-world difference, that's the true essence of isomerism. They are fundamentally different things. So, to make sense of this whole molecular masquerade, chemists came up with a classification system. It's basically how we categorize the different ways these doppelgangers can wear their chemical disguises. So these are the big ones for structural isomers. You've got chain isomerism, where the carbon skeleton itself is different. Then there's positional, where something just moves to a different spot. Functional group isomerism, where the atoms actually rearrange to make a totally different kind of VIP group. And finally, metamerism, which is a little more subtle. So let's just zoom in on the first 2. Chain isomerism is exactly what we saw with butane. The actual carbon backbone changes its shape. Think a 6-carbon chain versus a 5-carbon chain with a branch. Same formula, totally different skeleton. Positional isomerism is a bit more subtle. The skeleton stays the same, but something attached to it, like say a double bond, moves from one carbon to another. The backbone's identical, but where that key feature is located changes everything. All right. To really see positional isomerism in action, let's look at a classic example. And it involves one of the most important molecules in all of organic chemistry, the benzene ring. So let's play a quick game. If we take a benzene ring and we stick 2 identical groups on it, how many unique ways can we arrange them? How many positional isomers can we possibly make? The answer is just 3. That's it. You can put them right next to each other. Chemists call that the ortho position. You can put them one carbon apart, which is meta, or you can put them directly opposite each other, which is para. Any other way you draw it is just one of these three rotated in space. Only three possibilities. Okay, let's raise the stakes. What happens now if we add a third identical group to the ring? How many unique arrangements are possible this time? And surprisingly, the answer is still 3. The geometry of that flat ring is so constrained that there are only 3 distinct ways to place them. You can have them in a 1-2-3 line, a 1-2-4 pattern, or the perfectly symmetrical 1-3-5 arrangement. All right, final round. We've got 3 groups again, but this time 2 are the same and 1 is the odd one out. How many isomers does this one little change create? The number of possibilities doubles to 6. Isn't that wild? It really shows you how quickly complexity can pop up from just a simple change. By making just one of those groups different, we've broken the molecule's symmetry, and that unlocks a whole new set of possible molecular identities. So let's bring all this back to where we started. We kicked this off by asking about a molecule's true identity, and I think we've seen it's way more complicated than just a list of atoms. And that's really the bottom line. A molecular formula is just the parts list. The structure, that's the blueprint. It's the unique arrangement of those parts in 3-dimensional space that dictates everything: the molecule's name, how it behaves, and ultimately its role in the universe. And that just leaves us with this incredible thought, right? If just rearranging the exact same set of atoms can create substances with completely new properties, what amazing new materials or medicines or technologies are just sitting there, waiting to be discovered, hidden inside the formulas we already know?